Welcome back. In this video, we're going to introduce the polar coordinate system. Our objectives here are to introduce the polar coordinate system. We're going to plot points on the polar coordinate system. We're going to display multiple representations of polar points. And we're going to do some coordinate conversion. We're going to convert from polar to the rectangular system and from our rectangular system to the polar system. So our first objective here is to introduce this polar coordinate system. So far we have represented graphs of equations as collections of points x and y on the rectangular coordinate system, or the Cartesian plane, where x and y represent a directed distance, or distance, from the coordinate axes, our x and y axes. Well, here we're going to study the polar coordinate system. And the polar coordinate system has a little bit different setup. We will have an origin, or a fixed point, called the pole. And we'll construct from that origin an initial ray called the polar axis. So the polar axis is what we would remember as our x-axis from the rectangular coordinate system. Well, each point P in the plane is assigned a particular coordinate r and theta. So instead of going like an x distance and a y distance, our r distance is going to be our x distance, but our theta is going to be an angle instead of maybe a distance on the y-axis. Our r is a directed distance from our pole to some point P, and our theta is a directed angle counterclockwise from the polar axis. Instead of an x and a y, now we have some distance r from the origin, from the pole, and we have some angle, some theta, from the polar axis. And what that does is that creates a circular kind of polar plane, if you will. Our polar axis is what was formerly our x-axis, and each one of these is a theta, or some angle, from that polar axis. So if you're looking at this and you see these angles here of pi over 6 and pi over 4 and pi over 2, if you see these angles here of pi over 6 and pi over 4, pi over 2 and pi, and you see the unit circle, you are definitely on the right track. There's definitely a connection between our polar coordinate system and the unit circle. So our pole here is right at the center. We've got our polar axis, and then all of our angle thetas as we proceed around the polar axis. And these points here, the 1, 2, 3, 4, that is our directed distance from the polar axis. So real quickly, if I wanted to plot a point like 3 pi over 4, would be here. Our distance 3, and our theta is pi over 4. So I just plotted the point 3 pi over 4. So let's go ahead and plot some points on the polar plane. Our first point we're going to plot is 2 pi over 3. So I can see 2 on my polar axis, and that's going to go in a circular fashion, and then my angle is pi over 3, and I've plotted our first point, point A. This point B, 3, negative pi over 6. So now I'm going to move in the negative direction from 3, pi over 6 units. And point B, we'll do that one in red for you. We did 3, so that is going to be there at 11 pi over 6, or negative pi over 6. And our third point, C, is 3 11 pi over 6. Well, 11 pi over 6, we're going to go all the way around the unit circle, and we're going to end up over here, or around the polar plane. And we end up at the same point as B, so B and C are located on the same location there. So as you saw in the last sample, we can have multiple representations of points. In the rectangular plane, each x and y has a unique representation, but the polar plane, because of its circular nature, there can be multiple representations. R theta and R theta plus 2 pi can represent the same point. So another loop around the polar plane. Similar to Chloe Kim doing multiple revolutions in her half pipe. She does 720s and 900s and 1080s, 2 loops, 2.5 loops, 3 loops. We can do the same thing around the polar plane. So another way to obtain multiple representations of a point is to use negative values for r. Because r is a directed distance, the coordinates r theta and the opposite, or negative r theta plus pi, represent the same point. Think of this as reflecting across the pole. So to go negative r theta, a negative r might be 2 units in that direction. So that might be a negative 2. We can represent those points in a couple different ways. In general, r theta can be represented as r theta, or r theta plus or minus 2n pi. N is the number of revolutions around. Or negative r theta plus or minus 2n plus 1 pi. Now n is an integer. The pole is represented by 0 theta, where theta can be any angle. So let's see if we can make some sense of all this. Let's plot the point 3, negative 3 pi over 4, and we'll find 3 additional points. We'll find 3 additional polar representations of this point in negative 2 pi to 2 pi. So we're only going to do 1 revolution, either forwards or backwards, around the polar plane here. 3, negative 3 pi over 4, I'll call that point A. So 3 is my directed distance. My angle, negative 3 pi over 4, 1 pi over 4, 2 pi over 4, negative 3 pi over 4. Let's see if we can sketch that out. 1, 2, 3. And that is going to be located right there. That's going to be our point A. And now we want to represent this in different ways. Well, we can see here our first point, we went that way. So the second point, we can go ahead and cruise the other way and represent that as in the red. So our first option would be to call that 3, 5 pi over 4. Another way to look at this is we could see that as negative 3. But negative 3, we can't call it 5 pi over 4. It's actually going to end up kind of over here. We would call it negative 3 pi over 4 is still that location A. So while we think about reflecting it over, it's here, but it's kind of sucked into the black hole, so we're still going to plot it there. And our third option can also be negative 3, but now if we go, remember we're here at pi over 4, well, this location is a negative. So think about it this way. So that is a negative 7 pi over 4 rotation to that point, kind of that pseudo negative 3 point there. So negative 7 pi over 4 are all representations of point A on our polar. Let's complete another sample problem. Take a look at sample 3. We're going to plot the point 2, negative 5 pi over 6, and then we'll find 3 additional polar representations of the point between thetas of 2 pi and negative 2 pi. Let's begin by plotting the point, 2, negative 5 pi 6 radians. So our directed distance is 2. We're going to go negative 5 pi over 6 radians, which would take us to this particular point. So we've gone negative 5 pi over 6 radians, and we've plotted our particular point. We'll just call that point B. But now we need 3 additional points. Well, our first point, fairly straightforward. We can move in the positive direction. So our directed distance 2, move 7 pi over 6 radians to get us to B. And we've got our first point, which is at a directed distance of 2 and 7 pi over 6 radians on the polar plane. Our second point might be a little bit more challenging. Now we have to change our directed distance from positive to negative. So think about a negative 2 directed distance. Well, we have to reflect pi radians across the polar plane. So if we're going to go negative 2, we've got to backtrack, if you will, to this point over here, which now is negative 2 and pi over 6, which is still really this point B, but we're kind of viewing it here, but we're really located at B. We're just going to negative 2 units, and we end up at pi over 6. So again, if our R is negative 2 and we were at pi over 6 here, well, now to get there, we have to go negative 11 pi over 6 to get back to that particular point. So we have our third point at negative 2, negative 11 pi over 6. Moving on to our fourth objective of coordinate conversion. To establish the relationship between polar and rectangular coordinates, let the polar axis coincide with the positive x-axis and the pole with the origin. Because our ordered pair of the rectangular plane x and y lies on a circle of radius r, it follows that r squared equals x squared plus y squared. Moreover, using our definition of trigonometric functions, it implies that the tangent of theta is equal to y over x, where tangent would be our polar and y over x is the rectangular version. Cosine of theta is equal to x over r. If we multiply both sides by r, we get r cosine of theta is equal to x. So the polar equivalent of the rectangular x is r cosine of theta. And we can do the same thing with sine, multiplying both sides by r. We get r sine of theta equals y, and the polar equivalent of our rectangular y is r sine of theta. Over here on the right-hand side, I've written a little bit of table. You may want to copy that down, where the polar and the rectangular are compared and are polar and rectangular equivalent. So we'll be able to go back and forth between the two. So our ordered pairs are directed distance r and our angle theta in radians, or the polar or the rectangular equivalent of x and y, where r squared is equal to the rectangular equivalent of x squared plus y squared, and square rooting both sides, we get r is the equivalent of the rectangular square root of x squared plus y squared. The polar version of x is r cosine of theta, and the polar version of y is r sine of theta, and tangent is y over x. Either of those, though, of course, we know that also as slope. So let's do some sample problems with this. We'll convert polar coordinates to pi, so our r and our theta of 2 and pi radians, to rectangular coordinates x and y. Since we know x is r cosine of theta and y is r sine of theta, we can substitute our r value of 2 and our theta value of pi into r cosine theta and our sine of theta and get values for x and y. X is equal to r cosine of theta to cosine of pi. Using our unit circle, the cosine of pi is -1, so 2 times -1. So we get an x value of -2. So we know in our rectangular, we've got an x value of -2. Y is our sine of theta. Again, our r is still 2, and our theta is pi, so we'll replace theta with pi. On our unit circle, the sine of pi is 0. 2 times 0 is 0, so our y value is 0. And we get a rectangular ordered pair of -2, 0. We can do the same thing again with a new ordered pair of 4, a directed distance r of 4, and a theta of pi over 3. So our x value now is r is 4, and the cosine of pi over 3. Going to our unit circle, the cosine of pi over 3 is 1/2. So we have 4 times 1/2, and we get an x value of 2. We're halfway to having our rectangular ordered pair. We just need to find the y value, and y is equal to r sine of theta. Y equals our r here is 4, and the sine of pi over 3. Going to our unit circle, the sine of pi over 3 is the square root of 3 over 2, and that gives us a value of y equals 2 times the square root of 3. 2 times the square root of 3 is the square root of 12, or about 3.5. In sample 5, we want to convert the point -1, 1 to polar coordinates. So now we're in the rectangular. We have an x value and a y value. We can help ourselves out by possibly plotting this on the coordinate plane. Our rectangular value, we're here in the second quadrant at -1 for x and 1 for y. Since we have x and y, we want to substitute those values into tangent. So our tangent of theta is y over x. Tangent of theta, our y value is 1, our x value of -1. So our tangent is -1. We may go to the unit circle for this, and we see that we have tangent is negative in the second quadrant. And look at that, we're in the second quadrant on our coordinate plane. So let's work in quadrant 2, and tangent of theta is -1. Our theta here from our unit circle is 3 pi over 4. So now we just need to find the r value. We have our theta. So we've got half of our ordered pair is 3 pi over 4. Substituting our x values and y values in, we get -1 squared plus 1 squared equals r squared. 1 plus 1 is 2, is equal to r squared. So we get r is equal to the square root of 2. We have our polar version, square root of 2, 3 pi over 4. And that should make sense to us. If we think about that, realize again, go back to our triangle here where this is -1 unit on the x and 1 unit on the y. This is a 45, 45, 90 right triangle, which corresponds to our 3 pi over 4 radians, and x, x, and x root 2. So it totally makes sense that our directed distance is the square root of 2. And now if we're on the polar with, say, 1 and 2, and square root of 2 is somewhere between 1 and 2, and of course 3 pi over 4 is going to open up about here, and we will be in this particular location, somewhere between 1 and 2, and at 3 pi over 4. Our final sample, we want to convert 0, 2. our x and our y to polar, I bet you can do this visually. If we plot our x and our y, we're going to be up here at 0, 2. Our directed distance, our r value, we want an r and a theta. Well, our r value here, this length from the pole or from the origin is just 2. So our r value is going to be 2. And look at that location. Where are we located? We're 90 degrees. So this is going to be pi over 2 units. We have just converted that from rectangular to polar. So our polar, that guy is going to be right there. This is 1 and that is 2. And you'll get some more practice with this when I see you in class.